Welcome to Chemistry with Caroline. In this video, we're going to look at ring expansion rearrangements in E1 reactions. So you can see here that we're starting on the reactant side with a four-membered ring. We have a starting material with a bromine leaving group on it. And the top two products also have four-membered rings, and the skeletal structure of those products is the same as that of the starting material. So those would be expected products. The bottom two products, however, have five-membered rings. So the skeletal structure is different than that of the starting material, and that tells me that there was probably some type of rearrangement reaction that occurred. So the presence of unexpected products means that there was some sort of shift that happened. And in this particular case, it was a ring expansion because I went from a four-membered ring to a five-membered ring, so smaller to bigger. On the next slide, we'll look at the mechanism for how this type of ring expansion occurs. Here's our reaction scheme with just the unexpected products drawn. We're going to show the mechanism for how these products occur. So my starting material already has a good leaving group on it in bromine, and it's on a secondary carbon, so it can leave from that secondary carbon. I'm going to use equilibrium arrows there because the leaving group leaving is a reversible reaction. So when that leaves, I generate this initial carbocation intermediate, and then I have bromide as a leaving group. Now I'm going to number this intermediate that we just made so we can keep track of what's happening. So I'm going to start at the carbocation and then just go around the ring here. So it doesn't matter how you number, this is really just to keep track. So our ring expansion occurs when the bond between carbon 2 and 3 jumps out to become a bond between carbon 3 and 1 to expand from a 4 to a 5-membered ring. So my arrow would start between 2 and 3 and it would end at carbon 1, which is electron deficient. It has a carbocation on it, so it can accept electrons. I'm going to draw our product over here. So this is not a reversible arrow. The activation energy required for the reverse reaction is going to be really high and not surmountable. Most rearrangements will occur to give a more stable structure, so they're typically not reversible. So I'm going to number again here so we can keep track of what's going on. Now here is my carbon 1. That's the carbon that had the methyl group on it, right? It's now bonded to carbon 3. And then 4, and then 5. And then on the other side, it'll be bonded to carbon 2. Carbon 2 is no longer bonded to carbon 3, so it's lost electrons, and it is the carbocation in my new rearranged structure. Now that I can see this rearranged structure, I can see how those products formed. So the alpha carbon would be the carbon with the carbocation on it, and then the neighboring carbons that have protons on them would be where the double bond would form. So carbon 1 has a proton, we could call that carbon the beta position, and then carbon 5 is also adjacent to the alpha carbon. It's not equivalent to carbon 1, so we call that beta prime. So the double bond between alpha and beta would give me this product on the left-hand side, and that between alpha and beta prime would give me that product on the right-hand side. I'm going to redraw our intermediate so that we can show the mechanism and just have a little more room so it's not quite as crowded. So here's my base. In an E1 reaction, a lone pair of electrons from the base is going to grab a proton off of a beta position. The electrons between the carbon and the hydrogen at the beta position are going to fold down between the alpha and the beta carbon to make a new double bond and form your alkene. And so that, in this particular case, would give the beta prime position as seen there. So rearrangements tend to occur because they generate a more stable intermediate. In the case of ring expansions in particular, you're going from a strained ring that does not have those optimized 109.5 degree bond angles that minimize steric and electronic repulsion because of the size of the ring. So a four-membered ring has 90-degree bond angles. Expanding to a five-membered ring relieves a lot of ring strain and a lot of electronic and steric repulsion. So that's often the driving force between these particular types of ring expansions that you'd see. So this is looking at ring expansions with E1 reactions in particular. If you found this video helpful, please like, subscribe, and share with your friends. Thanks.